Hello everyone, my name is Amit. In this session, we will discuss about the PYQ which has come in the previous year IIT JEE Advanced papers, right? And especially we will take the recent year problems. For example, we will start from 2014 and it will go up to 2022. That means the previous year, this year. So this session will be useful for those students who are going to write JEE Advanced this year, as well as those students who are going to write this advanced paper next year. That means 11th going into 12th. The chapter name is Chemical Kinetics, right? So let's start the session. So the first question that we are taking is based on the order of reaction, and it has come in 2019 JEE Advanced paper 1, right? So in this question, the kinetic data is given, the concentration of A, B, C are given, and accordingly rates are given, right? You can see concentration of A is given in the first column, then concentration of B, then concentration of C, and then followed by rate of the reactions for these concentrations, right? These are the multiple experiments which we perform, right? So on the left hand side, the first column is the experiment number, right? We perform the multiple experiments to obtain the order with respect to each species. For example, in this reaction, there are 3 reactants, right? A, B, and C. You can read the question. So for you, I will read out. Consider the kinetic data given in the following table for the reaction A plus B plus C giving out product. Experiment number 1, 2, 3, 4, and various concentrations are given and various rates are given. Now the rate of the reaction for concentration A, B, and C you have to find out. It is given in the form of y into 10 raised to minus 5. So you will find out the rate and then you will compare the rate with this y into 10 raised to minus 5. So this is how you will find the value of y, right? So let's start solving this. What to do? First of all, you will assume order to be x, y, and z with respect to A, B, and C, right? Order is not given. We have to find out the order. So let us assume that the order with respect to A, B, and C are x, y, and z respectively, right? So let us assume that the order with respect to A, B, C are x, y, and z. So we can write the rate law expression R is equal to K, concentration of A raised to the power of x, concentration of B raised to the power of y, and concentration of C raised to the power of z, where x, y, and z are the order with respect to A, B, and C respectively, right? Now we have to find out the value of x, y, z, and k, the rate constant. Now how to find out? For that we are given the multiple experiments, experiment number 1, 2, 3, and 4. So we can develop 4 equations based on these data, right? We can develop 4 equations corresponding to each of these experiments, right? So for example, let us take the experiment number 1. So in experiment number 1, the concentration of A is given to be 0.2, concentration of B is given to be 0.1, and concentration of C is given to be 0.1, and corresponding to these concentrations, the rate is given to be 6 into 10 raised to minus 5. So we can form one equation, right? Let us write the equations in the next page. We can write R is equal to K times the concentration of A is given to be 0.1 raised to the power x, concentration of B is given to be 0.1 raised to the power y, and concentration of C is also given to be 0.1, so raised to the power of z. You can see here the concentration of A is given to be 0.2, then 0.1, and then 0.1, right? So we have taken these concentrations and we have raised it to the power of x, y, and z, which we have assumed to be the order with respect to A, B, and C respectively, right? Similarly, we can form 3 more equations based on the experiment number 2, 3, and 4. We are given the concentration of A 0.2, B 0.2, and C 0.1. So you can see here that concentration of A has been kept constant, 0.2 and 0.2. Concentration of C is also kept constant, 0.1 and 0.1. Concentration of B is varied from 0.1 to 0.2, right? And you can see the rate of reaction remains the same, right? Rate of reaction in the first one, this is given to be 6 into 10 raised to minus 5. Now, on doubling the concentration of B, rate remains same, right? So let us double this. So we can write rate is equal to K times concentration of 2 raised to the power X. B has been doubled, so 0.1 becomes 0.2. C has been kept constant, so 0.1 raised to the power of Z, and rate remains constant. So we can develop one more equation. So we have developed basically two equations, 1 and 2, based on the experiment number 1 and 2. Now let's go for the third experiment. In the third experiment, you can see here the concentration of A again remains same, concentration of B also remains same, concentration of C has been made to be twice. Now there is one error here. Instead of minus 5, this will be minus 4. The original paper contained this 1.2 into 10 raised to minus 4, right? So concentration of C, if you double it, the rate becomes 1.2 into 10 raised to minus 4. So we can write here rate is equal to K times concentration of 2 raised to the power X, concentration of 1 raised to the power Y, and concentration of C becomes twice, so 0.2 raised to the power Z, and the rate becomes 1.2 into 10 raised to minus 4. One correction here, this is minus 5. This is minus 5. So 3 equations we have formed. Similarly, we can form fourth equation based on this experiment number 4. 0.3, 0.1 and 0.1. That means B and C has been kept constant and C has been made 0.3 from 0.2. So 0.3, let us write 0.3 raised to the power X, 0.1 raised to the power Y, and 0.1 raised to the power Z. And let us see what happens to the rate. Rate is 9 into 10 raised to minus 5. So it becomes 9 into 10 raised to minus 5. So we have developed 4 equations. So using these 4 equations, we can find out the value of X, Y, Z and K, right? So let us find out. We can manipulate the equation 1 and 2. We can divide equation 1 from 2, right? So 1 by 2, if we do, what do we get? 0.2 to the power X, 0.2 to the power X. So it cancelled out, right? K and K also cancels. 0.1, 0.1, this also cancels out. So you get 1 by 2 raised to the power Y, and on this side 6 into 10 raised to minus 5, 6 into 10 raised to minus 5. So you get 1, right? 0.1, 0.1 gives 1, 0.2, 0.2 again gives 1. So these ratios will be 1. So you will be left with 1 by 2 raised to the power Y, giving out 1. So this implies that Y is basically what? 0, right? That means the order with respect to B is 0. So there is no effect of the concentration of B on the rate. That is why rate remains constant, right? Rate in 1 and 2 remains constant even if we double the concentration of B. So this implies that the order with respect to B is 0, and mathematically also we have obtained it to be 0, right? Similarly, we can divide equation 1 by equation 3, right? We can obtain, so 1 by 3 you see here, so K 0.2, 0.2, K 0.2, this cancels. 0.1, 0.1, this also cancels. So we are left with 1 by 2 raised to the power of Z, and in this side, if we divide this by 1.2 into 10 raised to minus 4, so we get 1 by 2. So this implies that Z is equal to 1, right? Similarly, we can divide equation 1 by 4. So we will get 2 by 3 raised to the power X is equal to 6 by 9. So 6 by 9 is nothing but 2 by 3, right? 3 to the twice, 3 to the 6 and 3 to the 9, so 2 by 3. So this again implies x is equal to 1. So we have obtained the order with respect to A, B and C. X has been found out to be 1, Y is 0 and Z is 1, right? So it has taken almost 2 to 3 minutes, right? Now there is one alternate method. Without forming these equations, we can easily find out the order with respect to A, B and C. That means X, Y and Z can be found out even without developing these equations. Just you see the kinetic data, what is given in the original problem, right? You see here, you focus on the experiment number 1 and 2 first of all. In experiment number 1 and 2, you can see the experiment number 1 and 2. In experiment number 1 and 2, concentration of A remains constant, concentration of C also remains constant. So we are simply doubling the concentration of B. Concentration of B we are doubling, and on doubling the concentration of B, rate remains constant. That means order with respect to B will be 0, right? So Y you can directly find it by looking at the data of the experiment, and it is simply what? 0. Why? Because on changing the concentration of B, rate does not change. So this simply implies that rate of the reaction does not depend on the concentration of B. So order with respect to B will be what? 0. Similarly, if you have to see the order with respect to A, that means if you have to find out the X, what you can do? You see those experiments where B and C remains practically constant. B and C remains constant, right? So you can see here, you can see experiment number 1 and 4. If you see experiment number 1 and 4, B and C you can see they are constant. B and C, B is 0.1, 0.1, C is 0.1 and 0.1. What we are looking at? Experiments 1 and 4. Experiment number 1 and 4. In experiment number 1 and 4, the concentration of B and C remains constant. Concentration of A goes from 0.2 to 0.3. So 0.2 to 0.3 means what? How much times concentration has been multiplied, right? With what factor concentration of A has been multiplied? So you can easily see here, it is basically what? 0.2 into 3 by 2, right? If we multiply 0.2 by 3 by 2, we can easily get 0.3. So concentration of A has been multiplied by 3 by 2. You again see the experiment number 1 and 4. So 0.2 and 0.3, we are trying to develop with what factor concentration of A changes, right? So concentration of A goes from 0.2 to 0.3. So basically 0.2 has been multiplied by what? 3 by 2. Now if we multiply concentration of A by 3 by 2, look at the effect on the rate. What happens to the rate? Rate goes from 6 to 9. Rate goes from 6 to 9. So rate goes from 6 to 9 means what? What factor we can see here? 6 into, again you can see 3 by 2, you can get 9, right? From 6 to 9, that means again a factor of 3 by 2 is coming here. That means on multiplying the concentration of A by 3 by 2, rate is also multiplied by 3 by 2. So that simply implies that X will be equal to what? 1, right? Similarly, if you want to find out the order with respect to C, look at the experiments where concentration of A and B remains constant, right? So concentration of A and B remains constant. Let us see. So you can see this happens in experiment number 1 and 3. If you see the experiment number 1 and 3, the concentration of A and B remains constant, right? This is also 0.2. Here also you are having 0.2. This is also 0.1, this is also 0.1, right? So concentration of A and B remains constant. Now C, the concentration of C is basically what? Doubled. The concentration of C is doubled. Now see what happens to the rate. right? So rate changes from 6 into 10 raised to minus 5 to 1.2 into 10 raised to minus 4, right? Rate goes from 6 into 10 raised to minus 5 to 1.2 into 10 raised to minus 4. So you can see this is nothing but 12 into 10 raised to minus 5. You can write this to be 12 into 10 raised to minus 5. So you can see this is again doubled. On doubling the concentration of C, rate doubles. That means order with respect to C will be what? 1. So that means Z we can find out, right? Easily. It is 1, right? Since I am explaining, so it is taking time, but if you look at the experiments, right, you can easily find out. It hardly takes a minute, right? Within seconds you can find out what is the order of the reaction, right? Otherwise you have to form such equations, and by solving these equations you can find out X, Y and Z. Now the unknown value is still K, the value of rate constant. So let us see how to calculate the value of rate constant. We have obtained X, Y and Z. So we can put X, Y and Z value in any of these equations and we can find out the value of rate constant, right? So let us put this in equation number 1. Equation number 1, we have rate is equal to K times 0.2 power is 1, 0.1 power is 0, 0.1 power is 1, and the rate is given to be 6 into 10 raised to minus 5. So we can find out K into 2 into 10 raised to minus 2, right? 0.2 and 0.1 we will get 2 into 10 raised to minus 2, and this is equal to 6 into 10 raised to minus 5. So this implies that K is equal to what? 3 into 10 raised to minus 3, right? So K we are obtaining 3 into 10 raised to minus 3. Now we have obtained each of these unknowns, K, X, Y and Z. Now we can simply find out the rate. We have to find out the rate of reaction when the concentration of A is 0.15, concentration of B is 0.25 and concentration of C is 0.15, right? We have to find out the rate at this time when the concentration of A, B and C are these. So we can simply substitute these data in the equation 1. So let us keep, no, we can put this data in what? The original rate law, right? Since we have to find out the rate at these concentrations. So let us substitute the value of X, Y, Z here and A, B, C here. We have also obtained the K value. So let us write rate, we have to find out rate. So this will be K times concentration of A raised to the power X, concentration of B raised to the power Y, concentration of C raised to the power Z. So X, Y, Z we have obtained, and K is also 10 raised to minus 3. A value, let us see what is given to be A. Concentration of A is 0.15, 0.25 and 0.15. So this is 0.15 raised to the power X, 0.25 raised to the power 0 and 0.15 raised to the power 1, right? 0.15, 0.25 and 0.15. So by multiplying all these, you can get 6.75 into 10 raised to minus 5, right? If you multiply these, you will get, this is nothing but 1. Anything raised to the power 0 will give you 1. So this is nothing but 0.15 into 0.15. So you can get 3 into 10 raised to minus 3 into 15 into 15. So this will give you 225 and 10 raised to what? Minus 4, right? So 10 raised to minus 3, 10 raised to minus 4, you can get 10 raised to minus 7, and this gives us 675 into 10 raised to minus 7. So we can write it as what? 6.75 into 10 raised to minus 5. Now this has been given to be y into 10 raised to minus 5, and we have to find out the value of y. So you can see y is nothing but 6.75. So this is how we can solve this. So this is an easier problem with respect to other problems. This problem is very easy, right? It has come into JEE main also. It has been asked multiple times, not once or twice. So many times it has come into your JEE advanced and JEE main. So that's all about this. I hope you might have understood this, right? How to find out the rate. Again, let us have a look. What we were given the kinetic data, right? Multiple experiments have been performed and the data are given to be in this table, right? So 2.1. So all these data will give you the order with respect to A, B and C and the rate constant, right? You have two methods. First, by looking at the column, by looking at this table, you can find out the X, Y and Z. Or second, you can develop these equations and you perform mathematical operations, right? You divide these equations 1 by 2, 1 by 3, 1 by 4. You will find out X, Y and Z, and now you keep the value of X, Y and Z in any of these equations, you will get the rate constant. Once you get the rate constant, you have already obtained X, Y and Z, you can easily find out the rate at any given time for any given concentration, right? So we were given the concentrations 0.15, 0.25 and 0.15. So rate has been obtained to be this. Now we had to compare this. It was given to be y into 10 raised to minus 5. So y is simply what? 6.75. I hope this is clear now. So let's move ahead. Let us see the next problem. In this problem, you have been given an elementary reaction M to N and you have to find out the order of the reaction, right? The rate of disappearance of M increases by a factor of 8, right? So rate of disappearance of M minus dm by dt, this is given to be 8 times when you double the concentration of M, right? So minus dm by dt is basically your rate. You can write it as what? K times concentration of M raised to the power of X, right? So the new rate R dash is basically 8 times R if you multiply the concentration by what? 2. So if M becomes twice, rate becomes 8 times. So this is given. So you can see here, you can divide these two equations, right? So let's perform 2 by 1. So 2 by 1 you can get 8 into 8 is equal to 2 raised to the power of X. So X you can easily find out what? 3. So the previous problem was little bit difficult. This is quite easy. You develop the rate law, right? Assume the order with respect to M to be X, right? Now perform the operations. What is given? What is given? The rate of disappearance becomes 8 times on doubling the concentration of M. So if concentration of M is made twice, rate becomes 8 times. So that means you can easily find out the value of X just by dividing 2 by 1. So 2 by 1 you can get 8R by R, so 8. 2M by M, so 2 raised to the power X, K and K cancels out. So X you can easily find out 3. So this is the answer. Correct answer is B. Let's go for the next problem. Now this is a theoretical problem based on the Arrhenius equation, right? Multiple statements has been written and you have to choose the correct ones, right? According to Arrhenius equation, option A states that a high activation energy usually implies a fast reaction, right? You know that rate and activation energy are inversely related. Rate is directly proportional to what? Rate you can write what? K. Rate is K times concentration raised to the power what? Order. So if K is higher, we will say that the reaction is fast. And if K is lower, we can say that the reaction is what? Slow. So based on the value of K, right, any reaction, if it has higher rate constant, that means the reaction is faster. And if it has lower rate constant, that means the reaction is slow, right? So whether the reaction is slow or fast, you can easily determine once you know the value of rate constant. So now we have been given the activation energy. Now activation energy is basically related to rate constant. According to Arrhenius equation, you know K is what? A exponential minus EA by RT. So if you increase the EA value, EA is activation energy, R is gas constant, T is the temperature, A is the pre-exponential factor, and K is your rate constant. Now if you increase the value of activation energy, you can see K decreases, right? And if K decreases, what happens? The reaction slows down. But it is given that the reaction is what? A fast reaction. So this is wrong. Statement A is wrong. A high activation energy usually implies a slow reaction, right? But it is given to be otherwise. A high activation energy usually implies a fast reaction. So that means this statement is wrong. Now let us go for the option B. It says that rate constant increases with increase in temperature. So obviously you can see this Arrhenius equation, right? If you increase T, what happens? K increases, right? If you increase T, K increases. So that means the reaction is what? The reaction speeds up, right? So rate constant increases, right? So K value, K is the rate constant. It increases with increase in temperature. You can easily derive by using this equation, but it has been given in the theoretical form. This is due to a greater number of collisions whose energy exceeds the activation energy, right? Now you know that according to Boltzmann's distribution, if we plot the fraction of molecule with speed or kinetic energy, so something like this you obtain, right? Now this is the maximum fraction of molecule which is having this particular speed or kinetic energy, right? And this, suppose, is ET. This is the minimum energy which is required by the reactant molecules to cross the energy barrier, right? So this is, suppose, the energy barrier, which is what? Threshold energy. So you need extra energy EA, right? This is the energy of reactant molecule, the average energy of the reactant molecule, and this is the ET value. So in order to reach ET, you need this extra energy, which is said to be what? Activation energy. Now again read the statement. It says that this is due to a greater number of collisions whose energy exceeds the activation energy. Now you know what happens when you change the temperature, right? If you increase the temperature, this curve shifts something like this, right? This curve shifts something like this. You can see here. So this is the original equation, right? This is ET. ET is fixed. For any reaction, threshold energy is fixed. Now this is the average energy of the reactant under this condition. Now if we increase the temperature, on increasing the temperature, what will happen? On increasing the temperature, this curve shifts right and the maxima becomes flat, right? The maxima goes flat and the curve shifts towards the right, right? So now you can see a more number of molecules can cross the energy barrier, right? So this is the ET. This is the ET. The reactant molecules has to cross this ET. Previously, the fraction of molecule which is crossing the energy barrier is this. Now on increasing the temperature, what happens? A greater fraction is crossing the energy barrier, right? This is the area at temperature T, and this is the area which you are getting for temperature T dash, right? And T dash is higher than what? T. So if you increase the temperature, more and more number of molecules will cross this energy barrier, and that is why rate constant increases. So we can derive this statement using this Arrhenius theory, and which is based on what? This Maxwell's Boltzmann curve, right? If you increase the temperature, what happens? more number of molecules will cross the energy barrier, and that is why the rate increases, right? So the rate will increase. Now the statement C is given to be higher the magnitude of activation energy, stronger is the temperature dependence of the rate constant. You can read out, higher the magnitude of activation energy, stronger is the temperature dependence of the rate constant. Now this is extremely important, right? If activation energy is higher, the temperature dependence will be higher. This statement is correct. How to check that? You know that K is equal to pre-exponential factor A exponential minus EA by RT, right? Now you differentiate K with respect to temperature, you can get A exponential minus EA by RT into what? EA by RT square, right? So this is nothing but K. So you get K EA upon what? RT square. So if EA is higher, dk by dt will be higher, right? If activation energy is higher, then rate constant will depend more on the temperature, right? Since dk by dt you will get higher, right? So the same statement has been written, higher the magnitude of activation energy, stronger is the temperature dependence, right? So if EA is higher, reaction will be slow, but if you increase the temperature, rate constant will drastically increases, right? The increase will be more in magnitude, right? So if you increase EA, right, what happens? dk by dt goes high, right? dk by dt goes higher. That means K will depend more on what? Temperature. So this is also a correct statement. So option B and C both are correct. Now you go for the option D. It is saying that the pre-exponential factor is a measure of the rate at which collisions occur irrespective of their energy. So this is precisely correct. The pre-exponential factor does not is a measure of the rate at which collisions occur, right? You know that the rate constant is given by what? Collision frequency into fraction of molecule which are crossing the energy barrier into what? Steric factor. This fraction, this Z is what? Collision frequency. This is collision frequency. So it basically gives you the number of molecules, right, colliding per unit volume per unit time, right? What does Z indicate? Z is the collision frequency. Collision frequency gives us the number of molecules which are colliding, right, per unit volume per unit time. This F is basically the fraction of molecule which are having energy more than threshold energy. Fraction of molecule having energy more than equal to what? Threshold energy. For any reaction to occur, the reactant molecules must collide, and they should do so with a minimum energy called what? Threshold energy. If the reactant molecules are having energy higher than threshold energy, they will form the product, otherwise they will not form the product. This is the condition. Now apart from this energy barrier, threshold energy, we have one more factor, steric factor, which is basically considering the orientation of the molecules. For the reactant molecules to form the product, they should collide with minimum energy, as well as they should also have proper orientation, right? Orientation should also be proper in order to form the product, which is given by what? Steric factor. So you can read the statement, what is written? The pre-exponential factor, which is A, is a measure of the rate at which collisions occur, right, irrespective of their energy. So this pre-exponential factor includes what? This, the number of molecules which are colliding what? See here, the rate at which collisions occur. So this gives us the rate at which collisions occur irrespective of their energy. So this is also correct. So B, C and D are correct. So all these options are based on collision theory, which you have studied in chemical kinetics towards the end of the chapter, right? Which basically considers the effect of what? the orientation and the threshold energy on the reactant molecules, which is basically what? Derived from collision theory. So collision theory says that the reactant molecules, in order to form product, they must collide, and they should do so with a minimum energy which is higher than what? Threshold energy. That minimum energy is called threshold energy, and they must be properly oriented. So I hope this is clear now. So let's go for the next problem. So next we are given, again the same collision theory is related here. In a bimolecular reaction, the steric factor P was experimentally determined to be 4.5. We have just written over here, the steric factor P is experimentally determined to be what? 4.5. The steric factor is always determined from the experiment, right? Normally this P value is equal to 1 for simple reactions. For simple reactions, this P value, for very simple bimolecular reaction, P value is 1. But for most of the reactions, P is what? Less than 1. This is most common scenario. For most of the reactions, the steric factor is much less than 1, right? But for some reactions, which are called harpoon reactions, for them the P value is more than 1, right? If P value is less than 1, you need a catalyst. Why? Because if P value is lesser, rate constant will be lesser, right? If P value is less, rate constant will be less. So the reaction will slow down. In order to speed up the reaction, you need to increase the value of K, right? And so you need a what? Catalyst. Whenever P is less than 1, we need a catalyst. But if P is more than 1, no need of catalyst. We do not need a catalyst. Why? Because the rate constant is already high, right? Example of such reactions are basically the interaction between metal and the halogens, right? For example, potassium and bromine, right? If potassium reacts with bromine to form KBr, for this reaction, the P value is more than 1, right? So such reactions are very rare, right? Most commonly, what do we have? We have the scenario P less than 1, where we will need a catalyst. But for some of the reactions, for ionic reactions mostly, we have P more than 1, which are very fast reactions. So for such reactions, we do not need a catalyst. And for a very simple bimolecular reaction, P is said to be 1, right? And this is determined from the experiment. So based on this, we are given the next problem. It has come into your JEE Advanced 2017 paper 2. So you can see the recent trends are, that the questions from chemical kinetics are both theoretical as well as the calculations based, right? So you can see, you can have a look. In a bimolecular reaction, the steric factor P was experimentally determined, and it has been found out to be what? 4.5. Right? So P value is always found from experiments, and it is coming out to be what? 4.5. So P is more than 1. So what can we derive from this? If P is more than 1, we definitely do not need any catalyst, because the rate is already higher. For such reactions, for such ionic reactions normally, right, if P value is higher than 1, we do not need any catalyst, no need of catalyst. If P value is less than 1, we need a catalyst, but if P value is higher than 1, we do not need any catalyst. But now read out the statement, the correct options we have to find out. First statement is the activation energy of the reaction is unaffected by the value of steric factor. The activation energy, right, EA, it does not depend on what? Steric factor, right? EA has nothing to do with the steric factor, so this statement is correct, right? The activation energy of the reaction is unaffected by the value of steric factor. Now go for the second one. Now statement B is, since P is 4.5, the reaction will not proceed unless an effective catalyst is used. Now we have just said that if P is more than 1, you do not need a catalyst, but it is saying that you definitely need a catalyst. So definitely this is what? Wrong. We do not need catalyst, and it is saying that you must have a catalyst. So that is wrong. So this statement is wrong. Go for the option C. The value of frequency factor predicted by Arrhenius equation is higher than that determined experimentally, right? We can see here this p value is nothing but k experimental. It is a ratio of k experimental upon k theoretical, right? So this is what? A experimental exponential minus EA by RT upon A theoretical exponential what? Minus EA by RT. So you can see this value is given to be more than 1, right? You can see here this is p value is given to be what? 4.5. So 4.5 means this is more than 1. Now more than 1 means what? A experimental is more than what? A theoretical, right? So you can see this says that the value of frequency factor predicted by Arrhenius equation is higher than that determined experimentally. No, it is the otherwise, right? Now read out the statement given in D. The experimentally determined value of frequency factor is higher than that predicted by Arrhenius equation. So this is correct. If P is more than 1, then A experimental will be more than A, and if P is less than 1, which is generally the case, A experimental will be less than A. But in this case, for such reactions where P is much or simply greater than 1, you do not need any catalyst, and the experimental value of Arrhenius factor is more than that predicted by what? Arrhenius equation, right? So I hope you would have understood what I mean to say, right? And this is totally theoretical based on the collision theory. You can read out the statement. So option C was wrong. So C and D are basically opposite of each other, right? C says just contrary to what happens, right? C is saying that A experimental should be less than A, and D is saying that A experimental should be more than A. So option D is correct. So correct options are what? A and D, right? So let's go for the next one. Now read out the question. For a first order reaction, A gives out 2B plus C at constant volume and temperature. Now whenever volume and temperature are constant, pressure becomes directly proportional to what? Number of mole. According to ideal gas equation, PV equal to nRT. If pressure and temperature are kept constant, if volume and temperature are kept constant, pressure becomes what? Directly proportional to number of mole. Now we can derive this. Now read the subsequent part. The total pressure at T equal to 0 and at time T are P naught and PT. Initially only A is present with initial concentration what? A naught, and T 1/3 is the time required for the partial pressure of A to reach 1/3 of the initial value. Now the correct statements are, so basically 4 graphs has been given which you have to find out. So for finding out which one is correct graph, you need to obtain the equations. How to obtain the equations? So you would have studied the topic how to monitor the progress of a reaction, right? Using pressure, using volume, using titration, right? Using optical rotation. So those methods you have studied. So simply pressure based equation we have to develop. So let us write down the equation A to 2B plus C. First of all, write down the chemical equation. A gives out 2B plus C. At T equal to 0, the pressure is given to be P naught. B and C are absent, right? At T equal to 0, products will be absent. So at time T, let us say that X mole or in terms of mole, if you would have written, we would have said X moles, but we are starting with partial pressure since pressure is given in the problem, right? So let us say that a drop of X has occurred in the partial pressure of A. So this will be what? 2X, and this will be X. And total pressure is given to be PT. At time T, total pressure is PT. According to us, this is P naught minus 2X. So this is P naught minus X. P naught minus X P naught minus x plus 2x plus x. So you can get what? P naught plus 2x. Now x you can obtain Pt minus P naught by 2. Right? X is found out to be what? Pt minus P naught by 2. Now we know that K is what? 2.303. So let us see what is being plotted. ln. So let us write simply in terms of ln. So this is 1 by T ln starting pressure, which is P naught, upon final pressure P naught minus x. Since the reaction is first order with respect to A, so we will go with respect to A. So we have to consider what? Partial pressure of A. So it is immaterial, it is irrespective of the total pressure, right? We have to always relate the rate constant with the partial pressure of A. So with partial pressure of A, we can write what? P naught minus x. We should not write Pt. We should write partial pressure of A at time t, and this is not Pt. Pt is the total pressure, right? Whereas we have to keep the partial pressure of A at time t. So partial pressure of A at time t is what? P naught minus x. So you can write here, this is P naught upon P naught minus Pt minus P naught by 2. So K you can write down 1 by T ln of 2P naught upon 3P naught minus Pt, right? So you can write down K as what? 1 by T ln 2P naught upon 3P naught minus Pt. Now you can look at the graph. They have plotted ln 3P naught minus Pt with respect to time. So let us obtain the equation in terms of ln 3P naught. So we can write this equation as Kt is equal to ln 2P naught minus ln 3P naught minus Pt, right? So from this you can see here ln 3P naught minus Pt is equal to ln 2P naught minus Kt, right? So this equation is the straight line equation, right? Y is equal to mx plus c. You can have a look. This is plotted on the vertical, time is on the horizontal. So slope will be minus k. This m is nothing but minus k. This intercept is nothing but ln 2P naught, and this is y, right? So clearly this is a straight line having a negative slope. So it should be a linearly decreasing graph. So option A is correct and option C will be incorrect, right? You can have a look once again. This equation is the equation of a straight line, right? Having intercept ln 2P naught and slope minus k. Since slope is negative, it is what? A decreasing graph. So it should be a straight line having constant slope and it should be negative. So option A is correct, option C will be wrong. Now we have to see how T1 by 3 varies with respect to A naught, right? Now you can read out T1 by 3 is the time required for partial pressure of A to reach 1/3 of the initial value. You have obtained the equation of K in terms of P naught and Pt. So write down K is equal to 1 by T ln 2P naught upon 3P naught minus Pt, right? This is the equation which we have just obtained. 1 by T ln 2P naught upon 3P naught minus Pt, right? And here T1 by 3 is the time required for partial pressure of A to reach what? 1/3 of its initial value. This is nothing but 1 by T ln partial pressure of, we can also write this as partial pressure of A at time t equal to 0 upon partial pressure of A at time t, right? So if T is T1 by 3, the partial pressure of A drops from what? Drops from P naught to P naught by 3. You can see here. T1 by 3 is the time required for partial pressure of A to reach 1/3 of its initial value. That means this this PA should be what? P0 by 3. So P0 A by 3 it should be. So what do we obtain? This is ln 3 divided by what? T1 by 3. So T1 by 3 we can see this is ln 3 by K. So it does not depend on the initial concentration, right? It does not depend on the initial concentration. It is basically what? Constant. So let us have a look. It should be a what? T1 by 3 versus A0 should be a horizontal line. But it is given to be a linearly decreasing graph. So this option B is wrong, right? This is an incorrect option. Since it is a decreasing graph, it should be a horizontal line. It should be independent of A0. Next, we are given rate constant versus A0. Now you know that rate constant does not depend on the concentration, right? So it should be a horizontal line. So this is correct. Rate constant does not depend on the concentration. So it should be a horizontal line. T1 by 3 should also be a horizontal line. You know that any time in which certain fraction of the reactants decompose, if the reaction is of first order, it is irrespective of the initial concentration. Any time fraction, any fraction or any percentage, in case of first order, it becomes what? Irrespective of the initial concentration, whether it is T1 by 3 or T1 by 2 or any T. So the correct options are what? A and D. So this is the solution of this problem. I think you must have understood this. So let's go for the next one. Next we have this. Consider the following reversible reaction A plus B, giving out AB, and the reaction is reversible. The activation energy of the backward reaction exceeds that of forward reaction by 2 RT. Let us say that the activation energy of backward reaction is EB, and it is the activation energy of forward reaction is EF. Then EB is equal to EF plus 2 RT. According to the question, this is given. The activation energy of backward reaction exceeds the forward reaction by 2 RT. So EB is nothing but EF plus 2 RT. So we can see here EF minus EB, which is basically delta H. It should be what? Minus 2 RT. Change in enthalpy, which is nothing but activation energy of forward reaction minus activation energy of backward reaction. It must be what? Minus 2 RT. That is according to this problem. Now the next, read out the next line. If the pre-exponential factor of the forward reaction is 4 times that of the backward reaction, that means AF is 4 times AB. Let us say that AF and AB are the pre-exponential factor of forward and backward reactions. Then according to question, we are given that AF is 4 times AB. Now we have to find out the value of delta Z naught. You know that delta Z naught is given by what? Minus RT of ln what? KEQ. Minus RT into ln KEQ. So basically we have to find out what? KEQ. For KEQ, we can write KEQ as what? Ratio of rate constant of forward is to backward. KF is to KB will give us KEQ. Now KF, according to RNS equation, this can be written AF exponential minus EF by RT divided by for KB we can write AB exponential minus EB by RT, right? So according to RNS equation, K is A exponential minus EA by RT. So KF can be written as AF exponential minus EF by RT, and KB can be written as AB exponential minus EB by RT. So you can see here this is nothing but AF by AB into exponential minus EF minus EB by RT. So basically what? Minus delta H by RT, right? So KEQ, you can see AF by AB is, sorry, this is AB, this is AB. So AF by AB is 4 and delta H is minus 2RT, so minus 2RT divided by RT. So you will get what? 2. So 4E square is the value of equilibrium constant. You can again have a look what we are given according to the problem. According to the problem, we are given EB is EF plus 2RT and AF is 4AB. We have to find out the value of delta Z naught. Delta Z naught is what? Minus RT ln KEQ, right? KEQ can be written as ratio of rate constant of forward and backward reactions. According to RNS equation, we can write rate constant as A exponential minus EA by RT. So you write it for forward as well as backward and then take the ratio. So it comes out to be 4E square. Now delta Z naught can be found out by what? Minus RT into ln 4E square. So RT value is given to be 2500. So minus 2500. Ln 4E square can be written as ln 4 plus 2. Ln E square will give you 2. Log of product will give you sum of logs. So ln 4 plus 2. Ln 4, for ln 4 we are given ln 2 is equal to 0.7, right? So ln 4 can be written as 2 ln 2 and 2 ln 2 means 2 into 0.7. So 2 into 0.7 means what? 1.4, and 1.4 plus 2 will give you what? 3.4, right? Ln 4 can be written as 2 ln 2. So let me write minus 2500. Ln 4 you can write ln 2 square and plus 2, right? So 2 times ln 2 is 0.7 plus 2 into minus 2500. So this is equal to minus 2500. This is 1.4, so it becomes 3.4. So 3.4 if you multiply, so multiply 3.4 here. So what do you get? 175. This is 85000.1. That means you get what? Minus 8500, 8500. So this is the answer. You have to find out the value of delta Z naught. So it comes out to be this, right? I hope this is clear to you now. So this was based on what? The equation for delta Z naught, which includes KEQ. For KEQ you can write KF by KB. So finally, by performing this mathematical operation, you can easily find out the value of what? Delta Z naught, and it comes out to be how much? Minus 8500. So I hope this is clear now. Let's go for the next problem. Next we have this. For the following reaction, the rate of reaction is given to be dp by dt kx, right? So the order with respect to x we can easily identify. This is what? First order reaction with respect to x. 2 moles of x and 2 moles of x are mixed with 1 mole of y to make 1 liter of solution. That means the volume of solution is 1 liter. So 2 moles of x means 2 by 1. 2 will be 2 mole per liter will be the concentration of x, and 1 by 1, 1 mole per liter will be the concentration of y. So if 1 is the volume, right, volume of solution is 1 liter, so mole is nothing but what? Concentration of the species. Now at 50 second, 0.5 mole of y is left in the reaction mixture. This is given, and we have to choose the correct statement out of the following, right? So this is given. Now what we can derive from this? Read this one first of all, right? Rate of reaction. Rate of reaction can be written as what? Minus dx by 2 dt is equal to minus dy by dt is equal to dp by dt, and this is given to be k times concentration of what? X. This is given. For rate of reaction we can write down this expression, right? And rate of reaction is given to be k times x, right? They have given in terms of dp by dt, but we can also write in terms of dx by dt and dy by dt. right? Simply these coefficients we have to take care of, right? So coefficients will be taken care of whenever we are writing down the expression of what? Rate. So for x coefficient is 2, so we have 2 here. For y coefficient is 1, so 1. For p coefficient is 1. So 2, 1 and 1 are basically denoting the coefficients of x, y and p in the balanced chemical equation which is given in the problem. Now let us start the reaction. 2 moles of x and 1 mole of y has been mixed and allowed to react, right? And at t equal to 50 seconds we are given that 0.5 mole of y is left. So let's write down the chemical equation once again. 2x plus y is giving out product. T equal to 0, at t equal to 0, you can see 2 moles of x and 1 mole of y are mixed. So that means 2 and 1, p is not given. At t equal to 50 second, you can see at t equal to 50 second, what happens? At t equal to 50 second, 0.5 mole of y is left. 0.5 mole of y is left. That means what? That means 0.5 has been decomposed. So basically in t equal to 50 second, y goes from 1 to 0.5. If y goes from 1 to 0.5, that means 0.5 moles of y has been reacted. Now if you react 1 mole of y, 2 moles of y will be reacted. So if we are having 0.5 moles of y as reacted amount, so the reacted amount of x will be what? 2 minus 2 into 0.5. So basically we are obtaining what? 1. So when y is becoming half, x is also becoming half. That had to be, right? It was already known to us. Why? Because the coefficients are 2:1. So the half-lives will also be what? Equal. Since the amount of the species are taken in the ratio of their stoichiometric coefficient, so half-lives had to be equal and they are given here, right? So half-life is basically what? Half-life of x is found out to be 1. Half-life of x we can find out, this is what? 1. Sorry, half-life is how much? 50 seconds. Since in 50 seconds x is going from 2 to 1, right? In 50 seconds the concentration of x decreases from 2 to 1. So that is why half-life of x is what? 50 seconds. Since in this time half of the x is decomposed, so this is the meaning of half-life, right? Half-life is the time in which half of the reactant is decomposed. So half of x is decomposed in 50 seconds. That means half-life of x will be 50 seconds. Now let us read the next one. So option B is correct, right? Half-life of x is 50 seconds. This is very simple, right? Half-life of x is 50 seconds. Since half of reactant molecule x has been decomposed, so 50 half-life we can easily find out. Now we have to find out the rate constant. Now you know that rate constant, right? Half-life of x can be written as what? Half-life of x, t half of x, can be written as ln 2 divided by rate constant of x. Now rate constant of x can be given as twice of the rate constant of reaction, right? So this can be written as ln 2 by 2k, right? Since the coefficient is 2, so rate constant of x will be multiplied by what? This. So rate constant of x is twice of the rate constant of reaction, and rate constant of the reaction is given to be k. So half-life of x is given to be what? ln 2 by 2k. Now ln 2 by 2k, half-life of x we already know. 50 seconds is equal to ln 2 by 2k. So k can be written as ln 2 by 100. So ln 2 is nothing but 0.693 divided by 100. So we will get 6.93 into 10 raised to minus 3, right, per second. So rate constant of the reaction should be 6.93 into 10 raised to minus 3 per second. Now let us see what is given in option A. In option A, it is given to be 13.86 into 10 raised to minus 4. So clearly this is wrong. So option A is wrong, right? Since we are obtaining the rate constant as 6.93 and it is given to be what? 13.86. So clearly this is wrong. Now we have to find out at 50 second what is minus dx by dt, right? Minus dx by dt. Now you know that minus dx by 2 dt is k times x. For option B we are going minus dx by 2 dt is nothing but k into x. Now we have to find out the minus dx by dt at 50 second. That means concentration of x must be kept at 50 second, right? At 50 second, what is the concentration of x? You can see here the concentration is what? 1, right? So k into 1, so it is nothing but k. K we have already obtained, 6.93 into 10 raised to minus 3. So minus dx by dt can be written as twice of this. So it can be what? 13.86 into 10 raised to minus 3 mole per liter per second, right? So this is given 13.86 into 10 raised to minus 3 mole per liter per second. So option C is correct. Now in option D it is given to be what? Minus dy by dt at 100 second is equal to this. So you must find out what will be the concentration of x at 100 second first of all, right? What will be the concentration of x at 100 second? We have already calculated x at what? 50 second from the given amount of what? Y. Now let us calculate what will be the concentration of x at 100 second. So 100 second is what? 2 times t half. T half is 50 second. T half is 50 second and your time is given to be what? 100 second. So 100 seconds is what? 2 times t half. 2 times t half. Now in one half life, the concentration of x, in one half life, concentration of x goes from what? 2 to 1. In 1 t half, that is 50 second, right? In 50 second, the concentration of x goes from what? 2 to 1. So in another t half, the concentration of x will go from what? 1 to 0.5. In 1 t half, see the 50 second we have already obtained half life. Now 100 second we have to find out what will be concentration of x. So for concentration of x, you can see that 100 second is nothing but twice of half life. So in 50 second it is going from 2 to 1. So in another 50 second it will be going from 1 to 0.5. Now what we have to obtain? We have to obtain minus dy by dt. You can see here we have to obtain minus dy by dt, and you can check minus dy by dt is k times x, right? So minus dy by dt is nothing but k times concentration of x at 100, right? At 100, so k we have already obtained 6.93 10 raised to minus 3 into what? 0.5. So this you will get 6.93 into 0.5. So 5, 6. So we are getting 34.65 into 10 raised to minus 3. Let us check. 3.46. Yes, we can write this, right? So option D is also correct. You can see here, right? So if you multiply this, you will get this. So the correct options are what? B, C and D. The correct options are B, C and D. So it is simply based on the equation of rate of reaction and T half. What we mean by T half, and the formula for T half is what? ln 2 by k, k of the species for which we are looking at the half life. T half of x we are looking at, so we must divide ln 2 by the K of X, and K of X will be what? 2 times the K of reaction. So I hope it is clear to you now. So let's move ahead for the next problem. Next problem is this. This will be our last problem. So in this problem, we are given match the column. In list 1, we are given the decomposition of X profiles, right? Sorry, in column 2, we are given the graph, and in column 1, in list 1, we are given the rate. You can see here, the rate is given to be K times what? Access plus X. Access and K are constant. Access and K are constant, right? So access and K are constant, so the only variable is what? X. Next, we are given under all possible initial concentrations of X. So X can be anything, right? So if we want to obtain concentration versus time integrated rate law, then we must integrate this equation, right? Rate is given to be Kx divided by Xs plus X. Rate is given to be K times concentration of X divided by Xs plus concentration of X. This is given in the problem, right? So rate is given. We can integrate this. This R can be written as what? Minus of dx by dt, right? This can be written as minus dx by dt. This is K times X upon Xs plus X, right? So we can manipulate this. Xs plus X divide by X dx is equal to minus K dt, right? Now we can integrate this under the limit time equal to 0 to t. So at t equal to 0, let us say this concentration of X is X naught, and at time t, let us say that concentration is Xt, right? Now Xs is constant, so it will come out of the integration. So dx by X integrated from X naught to Xt plus dx integrated from X naught to Xt is equal to what? Minus K times t limit what? Dt integrated will be giving you t, so 0 to t. So this you will obtain to be what? Minus kt. Now dx by x will be integrated to be ln x in the limit what? X naught to xt plus this is dx integrated x, so x naught to xt equal to minus kt, right? So this is xs ln xt by x naught plus xt minus x naught is equal to minus of kt, is equal to minus of kt. So for kt we can write xs ln x naught by xt plus x naught minus xt, right? You can see the integration. From the differential rate law, we have to obtain the integrated rate law, right? This is neither first order nor zero order. Any of the order we cannot say by looking at the rate law, this differential rate law. So we must integrate this within limits. So let us integrate. For that we have to separate the variables. So xs plus x by x dx is k dt. Putting limit 0 to t, x naught to xt, we can obtain finally the equation as this. This is our integrated rate law for the given differential rate law. I hope this is clear now, right? Now let's see what we had to do. We have obtained the integrated rate law. We have to find out half-life. So half-life, how to find out? For finding out the half-life, you know that at t equal to t half, half of the reactant decomposes. So xt will be what? X naught by 2. You have obtained the differential, you have obtained the integrated form in this manner. So k into t half, you can write excess ln x naught upon x naught by 2 plus x naught minus x naught by 2. You can see here excess ln x naught by xt, x naught minus xt. So xt we have written x naught by 2. So t half we can obtain xs, so k t half is what? Xs ln 2 plus x naught by 2. So t half can be given as xs ln 2 times xs ln 2 plus x naught upon what? 2k. So we can see here that t half is independent of the initial t half depends on the initial concentration, and it is having a linear variation, right? It is having a linear variation. You can see here, you can write it as what? You can reframe this, since we have to look at the graph. You see here t half is given to be straight line. So t half versus x we have to find out, initial concentration of x. So t half versus x naught we have to find. So t half versus x naught. So we can write it like this. This is equal to xs ln 2, right? This is a constant. Since xs is constant, ln 2 is constant, plus x naught by what? 2k. So it is nothing but, if you plot t half versus x naught, what we will get? We will get a straight line having intercept xs ln 2. This will be xs ln 2 and slope equal to what? 1 by 2k. 1 by 2k is the slope. This is your m. This is of the form y equal to mx plus c. C is the intercept, m is the slope. M is nothing but 1 by 2k and c is nothing but xs ln 2, right? So this is the intercept, and tan of this angle we have what? 1 by 2k. So clearly first option is correct. So you can see that for 1 we can write what? P. For 1 we can write P. Now can we have Q? Half-life versus initial concentration. You can see half-life is independent of initial concentration. So this is basically corresponding to what? First order. For first order, half-life does not depend on the initial concentration. Since half-life versus initial concentration is a horizontal line, so this indicates that it follows the first order kinetics, right? Now let's go for R. R initially follows first order kinetics and then follows what? Sorry, initially it follows first order kinetics, since R is k times concentration of x raised to the power n. You can see initially rate is directly proportional to x. So initially it is following first order kinetics, and then rate becomes independent of the initial concentration. That means rate does not depend on the concentration of x. So this is nothing but zero order. So initially it is first order and then it is what? Zero order. Now this is a very famous case for lower concentration of x. You must have studied that decomposition of gas at low pressure follows first order kinetics, whereas at high pressure it follows zero order kinetics. So we can see here the rate equation is given to be this. So first can be matched with R as well, right? So apart from P we can give R also, right? Q is the special case, right? Q is the special case, but R is the general case, right? For S, you can see X is linearly decreasing with time. So this means it is following what? Zero order kinetics, right? For this, you can see ln X decreases linearly with time. That means this is also what? Corresponding to first order. Again, have a look. P versus initial concentration is given, that we have obtained, right? Q is basically corresponding to first order, but we know that one does not say anything about the order, right? It can be anything. So it is not first order, it can be first order, it can be zero order, it can be any order, right? Next, R is corresponding to what? It can be corresponding to first order as well as zero order. So one can be matched with R as well. Next, S corresponds to zero order. Why? X is linearly decreasing, so that corresponds to what? Zero order. For zero order kinetics, you know AT is what? A naught minus KT. So concentration decreases linearly with time. Similarly, for first order, you know concentration decreases exponentially with time, right? A naught exponential minus KT. But if you take ln, so ln AT gives us what? Ln A naught minus KT. So ln AT basically decreases linearly with time. So this is corresponding to first order. So T corresponds to first order, S corresponds to zero order, R can correspond to any order, right? And Q corresponds to first order, and P is again any general case we can have. Now check the list 1. List 1, second option we are being given where initial concentration of X are much less than Xs. That means X is much less than Xs. Initial concentration of X are much less than X. That means what we can say? We can say Xs plus X can be written as what? Xs, right? Approximately Xs. See, if initial concentration X is much less than Xs, that means Xs is very high. So Xs plus X will be giving you Xs. That means this can be written as K times X divided by Xs. So this is nothing but K dash times X. So that means the reaction follows what? First order kinetics. K and Xs are constant. So K by X dash will give you another constant K dash. So X is raised to the power of 1. That means this is what? First order. So this corresponds to first order. Now if it is corresponding to first order, that means option 2 can be matched with what? Option 2 can be matched with Q and then what? T. So option 2 can be matched with Q and T, right? You can see Q and T options corresponds to first order. So in this case we are obtaining what? First order. If initial concentration of X is very less, Xs plus X can be written as Xs. So it, under this limit, it tends to what? First order. Similarly, let us go for the third one. In third one, X is much higher than Xs. Initial concentration of X is much higher than Xs. That means we can write what? X plus Xs almost equal to what? X. So we can write here K times X upon what? X approximately. So what we obtain? We obtain K. That means the reaction follows what? Zero order kinetics. So this corresponds to zero order kinetics. Now zero order kinetics means which option we should match with? It should be matched with what? R. So third should be matched with R. Sorry, not R. It should be matched with S. Zero order we are getting, so it should be matched with what? S. Similarly, in 4 we are given to be initial concentration much higher than Xs, right? X is much higher than Xs. That means X plus Xs can be written as what? X. So it can be written as K times X squared divided by X approximately. So this is approximately equal to what? K times X. So again we are obtaining what? First order. Again we are obtaining first order. That means 4 should be again matched with what? Q and T, right? First order kinetics is given in Q and T. You can see here Q and T was corresponding to first order. So 4 should be matched with QT, 3 should be matched with S, 2 should be matched with QT, and 1 should be matched with PR. Right? Now let's see what is given in the option, right? A, B, C and D, what is given. So we have obtained what? 1 corresponding to PR, 2 corresponding to QT, 3 corresponding to S, and 4 corresponding to QT. Let's see once again. 4 is QT, 3 is S, QT and PR. PR, QT, S and QT, right? So now you have to go for the options, right? So 4 should be matched with Q and T, right? So these two we can discard. So 4 is matched with T. Next 3 should be matched with S, so obviously S. So both the options are still valid. Now 2 should be matched with Q and T. So 2 should be matched with Q and T. So option B is wrong here. So correct option is what? A. 1 should be matched with P. So that is already the answer up, right? P and R both can be matched with 1. So the correct option is what? A. So I hope you would have understood. Let me again revisit. This was the problem. We were given the rate, right? From the rate, we had to find out what? The expression of T half. So what we did? We integrated the rate law to obtain the, right, integrated rate law as this. Now for T half expression, what we should do? We should keep what? Xt to be x naught by 2. So this is the expression we are getting for T half, and this is nothing but a straight line having intercept axis ln 2 and slope equal to 1 by 2k, right? So corresponding to this, we had the option what? P. Next, it can also be matched with what? R. Why? Because it is a general case. At high concentration we are getting 0 order, lower concentration we are getting first order. So it can be matched with R, right? So P and R. And next, for 2 and 3, 2, 3, 4 are the special cases. In list 1, 2, 3 and 4 are the special cases where the initial concentration of X is much higher than XS or much lower than XS. Both are the limiting case. We have to do approximation and we have to obtain the corresponding order. So in 2 we are getting the order to be 1, in 3 we are getting 0 order, and in 4 we are getting first order, right? In the list 2 we are given the corresponding graphs, right? So graph S corresponds to 0 order, graph T corresponds to first order, and graph Q corresponds to what? First order. Why first order? Because for first order we know that T half is nothing but ln 2 by k. So it is independent of the initial concentration. So it should be a horizontal line, right? So horizontal line is given, so it corresponds to first order. In S we are given what? Concentration to be a linearly decreasing curve, linearly decreasing straight line. So decreasing means what? It should be 0 order. For 0 order, integrated rate law is of the form AT is equal to A naught minus KT, or XT equal to X naught minus KT, right? We can write down XT is equal to what? X naught minus KT. So this is nothing but 0 order. Similarly, we are given ln X decreasing, and it is a straight line having negative slope. So this corresponds to what? First order. So we can match this with what? 4 and 2, where we are getting first order, and this can be matched with S where we are getting 0 order. So I hope this is clear now. So that's all from my side, right? So these are the problems which have come in your recent years, right? Starting from 2014 to 2022, I have included all these years, right? Whatever problems have come in JEE Advanced paper, we have almost included all of the questions. So that's all from chemical kinetics. I hope you will like it, right? So thank you. That's all.